Good evening, everyone. Again, we are warmly welcome you all to our IEEEXtreme workshop on how to get ready for a coding hackathon. Today, Mr. Pasindu Wijesena is with us with a pool of information on this workshop. So, Mr. Pasindu Wijesena is the co-founder and CEO of the AI team and who was also a member of the team that placed second in Sri Lanka at IEEEXtreme 15.0. So now the virtual stage is yours, Mr. Pasindu Wijesena, to get started.
Okay. All right. So hope I'm audible and you can see my screen. Can someone confirm?
Yes, you're audible and you're visible.
Great. Right. Thank you very much for the introduction. So, like our host mentioned, I'm Pasindu. I'm a fresh graduate from University of Colombo. I graduated in April, and right now I work as a software engineer at the AI team, and I'm also one of the co-founders there. And I have some history with competitive programming. So today I hope to share some bits and pieces of it with you guys to help you compete in competitive programming competitions. So let's jump in. We are going to start with the question. What number comes next? Now I need you guys to answer. So you can write the answer in the comments. So we have a sequence here. 1, 1, 2, 3, 5, 8, 13. What would be our next number? Okay, we have a few answers coming up. Everybody's saying 21. Oh. Any other answers, guys? So we have 19 coming up. Okay. Any more? So we have around 60 people. Guys, come on. Type in your answer. Okay, we have a name as well for this. Okay, so is it 19? No, you guys guessed it correctly. It's 21. And it is indeed the Fibonacci sequence. So for those who don't know, the Fibonacci sequence is a sequence where you get some term by the summation of the previous two terms. So here, if you see 3 plus 5 is going to be 8, 8 plus 13 is going to be 21, 13 plus 21 is going to be 34. And so this sequence we can define by these two rules. So the first term and the second term we define as 1. And then the nth term of the sequence, we define it as tn minus 1 plus tn minus 2. So I have another question. What is the 21st Fibonacci number? Can you guys answer this one? Again, you can type it in on the comments section. All right, so I will actually, I don't really want the answer. I want to know the way that you approach this. So if you were told to find out the 21st Fibonacci number, and how would you do this? So what we have is this information. We know that we can compute the nth Fibonacci number by the summation of the previous two. And so a good approach to compute the 21st would be to write the first 21st numbers. So here I've written 5 numbers in each row. So the 21st one is 10,946. Two guys wrote it on the chat. So yeah, so what we did here was we came up with some algorithm. So this was an algorithm that we made up in our mind. So we have we saw this pattern and then we created some rules that we can use to find out the next number. And then we came up with an algorithm where we try to write down every number in the sequence gradually, continuously, and up to the point where we come to this 21st number. So this is what we can call an algorithm. So if we try to write this in some sort of a pseudocode, we can write it like this. We can say that the first term is, we are going to start with T1 and T2 variables. We are going to set them to 1. And then we are going to repeat this operation 19 times. So at each iteration, what we are going to do is we have some variable Tx that is going to hold the sum of T1 and T2, right? And then we shift. So in T1, we are going to store the current T2 value. And in T2, we are going to store the newly computed Tx value. And when we repeat this for 19 times, we are going to end up with the 21st Fibonacci number. So I have another question here. So in which variable would we have the 21st Fibonacci number at the end of this small pseudocode? Would it be T1 or T2? Yep, it's going to be at the T2. So let's say we wanted to compute the third Fibonacci number. Then this value we here would be, so we have the first and second. This one would be repeat one time. And so for that one time, we are going to compute Tx. Then we are going to move T2 into T1. And Tx is going to be the third Fibonacci number. It's going to end up at T2. So after we repeat whatever the times that we want to repeat here, that is like if you want to find the nth Fibonacci number, we have to repeat this n-2 times. After the iteration, at T2 variable, we are going to have the result that we want. So this is an algorithm that is going to allow us to find the nth Fibonacci number. That is, if you replace this by n-2, and here you replace by n, with this algorithm, you can find the nth Fibonacci number. Okay, hope that is clear, and we are clear up to now. And if you have any questions, guys, don't hesitate to unmute yourselves and ask, or write it up on the comment section. Okay, now we are going to move forward. So what is competitive programming? It's a sport for computer programmers where we get questions similar to what we just saw. The questions could be easier than what we saw. They could be harder than what we saw, but in a competitive setting, we are going to get questions just like the one we saw. And so the competitors here have to come up with creative algorithms that can solve the problem. So in this case, we came up with this algorithm, which allows us to compute the nth Fibonacci number, right? And once we have the algorithm, whether we write it explicitly on some piece of paper or draw it somewhere, or just have it up in our mind, what we have to do next is to express that algorithm as a computer code. So we have to write a computer program that hosts this algorithm of ours, which is going to take input from the standard terminal standard input and output into the standard output of the computer. And so that source code is what we usually submit in competitive programming competitions. So there is a catch in competitive programming. So you can't just write any algorithm for whenever you are given with a problem. So your algorithm has to be correct. It has to be fast enough, and it has to be memory efficient. So let's see what these three things mean. So a correct algorithm is an algorithm that spits out the correct answer for any input in the expected input range. So I have restated our problem in this way. So we are being asked to compute the nth Fibonacci number, and we have also been given with some constraints. So n is going to be less than or greater than or equal to 1 and less than or equal to 10 to the power 9, that is 1 billion. So within this range, if we were given with any number n that is an integer, our program, our algorithm that is going to get converted into a program should be able to output that nth Fibonacci number. So let's say we were given with this question, and in the question we have some example test cases as well. So if you write some sort of program that just solves the correct answer for the given examples, then you might not score at all. There could be cases in some competitions where you can score, but in many cases, if you just try to solve for the given examples, it's not going to be enough. You have to come up with a general algorithm that solves this general problem across the constraints that have been given, right? So when we are coming up with the algorithm, for us, the n is not going to be just 5, 6, or 21. It's going to be any number between 1 and 1 billion in this case. Right. The second thing is whatever the algorithm that you come up with, it has to be fast enough. That is, when you submit your computer program that contains your algorithm, and the graders there, whoever the people who host the competition, they grade your algorithm by running the program. So your program must terminate within the given time limits. Usually in these competitive programming competitions, it's going to be like 1 second, 2 seconds, or at most like 5 seconds. So your program should terminate within the given time limits. And now you might wonder how this time limit thing appears. So let's see an example. So in this scenario, we have the same question, but now our constraints are a bit higher. So n can be as big as 10 to the power 18. That is a billion billions. So in this scenario, if we wanted to find out the Fibonacci, the billion billionth Fibonacci number, with the algorithm that we have right now, that is going to continuously compute one by one the Fibonacci numbers, we are going to have to find the Fibonacci numbers from 1 to the billion billionth number, or the 10 to the power 18th number. So in this kind of a scenario, let's say that we have some computer that is capable of doing a single operation, that is like finding a single number within 1 nanosecond. And so we are going to repeat this 10 to the power 18 times, right? And let's say that this whole operation is going to complete in 1 nanosecond. Then we need 10 to the power 18 nanoseconds to come up with the answer. So that is going to be a billion seconds. And usually in competitive programming competitions, you don't get that much seconds. It's the algorithm that you come up with is not going to always work. So what we have in here in this case is a brute force solution. That is like we took what was available to us and we naively said that we are going to compute one by one and come up until we come and meet the solution. So for this question, this instance of this question where the constraint is 10 to the power 18, our solution might not work. But if the constraint was 10 to the power 9, like we had in the previous one, then we would need just 10 to the power 9 nanoseconds. That would be a single second. So in that scenario, our algorithm is going to be fast enough. So now you guys have to understand what I mean by fast enough. So we need to consider these constraints. What are the input ranges that we have? What is the time limit that we have? And then decide whether whatever the algorithm that we are coming up is going to be efficient, fast enough, whether it's going to be fast enough for this specified problem. right? So I hope I'm clear on this one. Guys, do you have any questions? If you have any follow-up questions, you can ask now. Okay, looks like we're good. Right, so we are going to move to the next one. That is a memory efficient algorithm. So we want to write a correct algorithm. We want to write a fast enough algorithm. And the third thing is we need to write a memory efficient algorithm. That is, in these competitions, when our program is being run, we don't get unlimited amount of memory. So usually the memory is going to be constrained to like 256 megabytes, 512, 1 gigabyte, something like that. So to understand how this affects the solutions that we come up, let's take another example question. So here what we have is the same Fibonacci thing, but I have modified it a bit. So now what we get is a set of queries Q. And for each query Qi in this set Q, we need to compute the Qith Fibonacci number. And now we have been given with the constraint. So the set Q is going to be 10 to the power 5. So we are going to have a million queries. And in each one of those million queries, the Qi could be, this has to be Qi, not N. The Qi is going to be between 1 and 1 billion. So this is the question that we have now. And so here is an example. So let's say that the input query Q, the Q has 2, 10, 3, 21, and 5. So we have to write a program that is going to print the second Fibonacci number, the 10th Fibonacci number, third Fibonacci number, 21st Fibonacci number, and the 5th Fibonacci number. So this is going to be a single program that prints out these 5 numbers into the standard output. So let's see how we can approach this problem. Guys, so now let's discuss what are the approaches that we can use to solve this problem. And first of all, are you guys clear about the question? Do you have any questions regarding the question? Okay, looks like we are good. So now we need to come up with solutions. So I have 3 solutions in mind, but I'd first like for you guys to have a go at this. So let's start with the naive ones. You don't have to think a lot. Let's see what would happen if you go down certain paths. So would someone like to volunteer up and say an approach that we can use here? What would be the most straightforward way? Guys, it does not have to work, right? We are just trying to see what approaches can be taken, and then we are going to study if those approaches are going to work. So we need some approaches. Come on, I'm going to wait for you guys. Okay, nice. We have one. Okay, it's a direct message. So one solution says we are going to repeat what was there in the pseudocode for each item of this set Q. So what we had in the pseudocode was to find out the nth Fibonacci number, right? And so what our friend proposed was to do it for each QI. So what a simple program would be like, you're going to write that initial pseudocode into a function that gives out the Fibonacci number when you give it the parameters, the n as a parameter. And then in a loop, you feed in each QI. So now let's, guys, yeah. Okay, we have another one. Sort the array and find the biggest number. Calculate the Fibonacci sequence till that number. Nice. We could use recursion. Yep, we could use recursion. So Akash, so recursion would be used, like we can use recursion in for this one whenever you are given with some n. In order to compute the nth Fibonacci number, instead of writing in this iterative method, you can write a recursive function, right? So this piece we can replace with a recursive function. And so right now we have two approaches. So one is to have this put up in a function, have a loop that goes through each QI. And for each one of them, we are going to run that function. So it's going to compute the Fibonacci number. And then the next one is we are going to sort this array, find the biggest number, and calculate the Fibonacci sequence till that number. Do we have any other approaches? So Tushar, how do we, like, we want to display the output in this way. So how do you propose we, after we compute the Fibonacci sequence till that maximum number, what are we going to do? So we have the Fibonacci sequence pre-calculated in one side. And then what would we do to print this output? Nice. So we are going to save the Fibonacci sequence in an array. And then for each QI, what we have to do is to find the QIth element in that array, or QI minus 1th element in the case of zero index arrays, and then get the relevant answers. Nice. Do we have any more approaches? Okay, let's wait one more minute. Do we have any other approaches? Okay, so it looks like we are stuck with these two approaches right now. So let's discuss them. So the first approach, we are going to have like a loop, outer loop, that is going to iterate through each QI. And inside that loop, we are going to have our previous pseudocode. So it was this one. And then it's going to compute our answer. So in that scenario, now let's assume our constraints were these, right? So the size of our this number of queries we are going to have is 1 million, and the QI is going to be up to 1 billion. So let's say that whenever we are like thinking about solutions to these problems, you like something that you can do is to try to think about the think like apply the maximum value that you can put in over there. So in this scenario, let's say that we have 1,000,000 queries now, right? And then in each query, we need to compute the millionth Fibonacci number, right? Or the millionth, or the million minus one, or million minus two, something like very huge. Okay. So if that was the case, so in order to compute the millionth Fibonacci number, with our this approach, we need to take million steps. And as we discussed before, it's going to take us 1 second, right? So in order to compute a single answer here in Q, we are going to take 1 second, another second, another second, another second. And since the queue here is going to be million items long, we are going to take million seconds to find the answer. So the first approach that we discussed is not going to be fast enough, because we are not going to get million seconds to find the answer for the million queries in a competitive programming competition. And I'm not sure if million is going to be good in real life as well, because it might be bigger than the life expectancy of people. Okay, so we have another question. We are confused about the constraints, right? Yeah, so we have a question about the constraints. I'll explain it right now, and then we can move forward. So constraints is, let's say whenever we are given with this question, right? So this is a general question. That is, we don't have a number put up here for n, right? So whenever you write a computer program, you write it with a placeholder. So the n is going to be something someone else is going to input, right? In this case, in a competitive programming competition, the grader or the evaluator is going to input this n, right? So the constraint specifies the limit of that n. So it's going to input a number that is going to lie in this range. So n could be 1, n could be 2, n could be 5, n could be 10 to the power 18 minus 5, but n can't be 10 to the power 18 plus 1, and n is not going to be 0, right? So this is going to bound us. So this is going to say that, okay, you want to come up with an algorithm that is capable of solving the nth Fibonacci number, but you may also assume that n here is not going to be less than 1 or greater than, in this one, a billion billions, 10 to the power 18. Am I clear? So these are just some examples that like in a competition, they might, like whenever they are telling the problem statement, they would typically give us some example cases for us to understand the problem. But whenever they are evaluating our program, they are going to evaluate against these constraints. So they are not going to just give n equal the n 5, 6, and 21. It's going to be some number, some sort of a number between this range. And in these competitive programming competitions, they are not going to just evaluate for a single case. Usually, like at good competitions, your program gets evaluated at hundreds of thousands of inputs to see whether it is actually correct, right? So am I clear regarding the constraints part? Nice. Okay. And if possible, just send the message in a way that everyone can see, so everyone gets to know what the context is, right? Okay. So we are back to our original problem. So we discussed about two approaches. So the first approach was we are going to iterate through each qi of this, and in each one we are going to find out the qith Fibonacci number. And there's another question. I'll come to that after saying this. So if we do this in approach, that is like we are going to have an outer loop, and inside that we have that inner loop we had in the pseudocode. This is going to take, the top one is going to repeat 1,000,000 times. The internal one is going to repeat 1,000,000,000 times. So 10 to the power 5 into 10 to the power 9, that's going to be 10 to the power 14, right? And it's going to be, in our scenario, if we assume that an operation takes 1 nanosecond, it's going to take 1,000,000 seconds. So are you clear about this running out of time concept? The 1,000,000 seconds, because computers, their computing power is not unlimited, right? They are going to take some time to compute whatever the computation that we give them. So because of that limitation, our programs need to be fast. So the first solution that we discussed just now, it is not a fast solution for this problem. Is it clear to you guys? Do you have questions regarding the first approach? Okay, while you guys digest, I will get into the questions. Why can't it be equal to 1? It can be equal to 1. So like in here, the constraint said that n can be less than or equal to 1. So we're not going to have n equals 0 in this scenario of the problem. And we are not going to have any number greater than 10 to the power 18 in this problem. What if we exceed the limit, like in entering a number larger than the 10 to the power 9? So in this question, for this question, any number larger than 10 to the power 9 is going to be out of scope. If you come up with an algorithm that is capable of computing the answer for the number 10 to the power 9 and 1 and all the numbers in between, it's going to be enough. That's why I said that like it has to be just fast enough. We don't have to be the fastest one. But you said that it can't, sorry, if I said that it can't be equal to 1, sorry, it can be equal to 1. Great. Okay, so are we clear about the first approach and why it does not work? Do you have questions? Then we are going to come into the second approach. I'm going to wait another second, another minute. So guys, so when you write error handling and others, but uses less time to do the processing. So I have another message. We don't have to do error handling. That is like in these questions, if they say that this is going to be constrained to 1 and 10 to the power 18 or 1 and 10 to the power 9, you don't have to think about these two ranges. Like you don't have to think about any number less than 1 or any number greater than 10 to the power 9. It's just, you're just not going to get it as an input, right? You can just completely ignore them. Those inputs are not going to exist in this world for this question, right? And we had to write the program that is going to use less time, that is less enough or fast enough, right? Okay, so I'm going to discuss the second approach. Just before we move on, are you guys clear about why the first approach is not going to be fast enough? Do you have any questions? Okay, looks like we are good. So we are going to try the next one now. So the next approach is we are going to sort this queue. Okay, so by we are going to sort this queue, and then we are going to get the largest number there. And using that largest number as the upper bound. So since we have like the constraint here, like we can consider this that largest number as 10 to the power 9 in this case. Okay, so when we are thinking in general terms, when we don't have the values put up here, you design your program to work to the worst case scenario, right? That is, in this case, our worst case scenario is when the length of queue is 1,000,000, and in each QI, the QI is going to be 1 billion, right? So let's say all the values here are 1 billion, right? Then what we are going to do is to compute, and so we have a lot of 1 billions. Now, after we sort, we know the maximum value is going to be 1 billion. And so after that, we are going to compute all the Fibonacci numbers from 1 to the first Fibonacci number to the billionth Fibonacci number. And then we are going to store them in memory, in an array. Right, now let's just simplify this approach in this area as well. So let's say that you want to find the largest number in this array. In order to find the largest number in this array, what approaches do we have? Do we have to sort it? Or is there any other approach that we can use to find the largest number here? So we are in a sub question now. We want to find the largest number here, right? Like when creating the solution, like imagining the algorithm, we are going to assume that it is 1 billion. But in the practical case, if we want to find the largest number, what is the approach? So our friend here suggested that we can sort this array. Do we have any other better ways? Okay, we have a whole algorithm. By using inbuilt function. Okay, we have a message that says by using inbuilt functions. Okay, so whether or not you use inbuilt functions, they are going to at the end use up your computer's processing power, right? It's going to use the processing cycles. So it doesn't matter whether you write those functions by yourself or you use the inbuilt functions. The difference is going to be very minute, right? So let me check. We have so I got another answer, a comment that has a whole Python code. Tarana, can you post this to like everyone so that everyone can see? Okay. Manupa, yes, they are optimized as far. Like, let's say we have a inbuilt sorting function, right? The best you can do for a sorting function is something in the order of n log n operations. Okay, so if I wanted to find the maximum value here, and if I were to sort this array using an inbuilt function, it's going to use n log n operations. So if I had 10 to the power, I'll now switch to no, let's say we have 10 to the power 10 10 to the power 10 values, then it's going to be 10 to the power 10 into 10, right? But let's say there are ways that we can further simplify this. So if I wanted to find the largest value here, all I need is another variable that keeps track of the current largest value here. And I'm going to initialize it with 2, okay? And then I'm going to loop through this array. And whenever I find a number that is larger than the value we store in that current largest variable, I'm going to update this, right? So when I go through this whole array, it's going to take n operation, n steps, because I'm looping through each and every one. And by the time I get to the end, this variable here, the imaginary one, okay, the current largest one, is going to have the largest value. And so this operation is going to take us only something in the order of n operations, whereas the previous solution, if we were to use inbuilt functions to sort this queue, it is going to use n log n, right? So your so if n was a small value, then sure, it would not make much sense. But as n gets larger, as n becomes larger, n log n is going to be much bigger than n. So that's the difference. So in the end, when you are coming up with these answers, it doesn't matter whether you use inbuilt functions or custom built functions. What you have to think first is the algorithm, initial algorithm, right? Am I clear? Hey, Mark. Nice. Okay, we have, okay, Akash has already like written the approach where we can find out the maximum value in an array. And we have a whole program that computes some answer. I will not go to it because we have limited time today. So in the second approach, if we are in the second approach, what we are going to do is we are going to find the maximum value here, and we are going to compute all the Fibonacci numbers. So the first Fibonacci number up to the maximum Fibonacci number. So according to our constraints, it would be 1 billion. And we are going to store that in an array. Now, just as similar, like just same as our like processing capacity, the number of ticks we can process, the memory is also limited, right? We don't have unlimited amount of memory. So now let's do some assumption. Let's say that we can store a Fibonacci number up to the 1 billionth number in an integer, in a 4-byte integer, right? So we need 4 bytes to store a single value, and then we have a billion. So this is going to take us 4 billion bytes. And 4 billion bytes is 4 gigabytes of memory. So if we go down this approach, if we are going to pre-calculate all the Fibonacci numbers up to the maximum value, we are going to need 4 GB RAM. We are going to need a 4 GB RAM to store those values. And then we are going to have to go through each of these queue items and then fetch the array value and print it. So this is what I mean by meant that we need to come up with algorithms that are going to be memory efficient. So in most competitive programming competitions, we don't get that amount of memory. It's going to be like 256 megabytes, 512 megabytes, 1 gigabyte, in some rare cases, 2 gigabytes. So we have to deal with memory. So in competitive programming competitions, when you are writing these computer programs, first thing you have to do is you have to make sure that your algorithm is correct. It should generalize for all the input values in the given range, in given constraints, right? And the second one is it has to be fast enough. So we need to compute it within the given time limits and for the relevant constraints. So the algorithm might have to write to find the nth Fibonacci number in this problem and this problem are different. So for this one, I can just go on, move ahead with the algorithm that we just talked, right? With this one, this simple one. But if you want to go to up to 10 to the power 18, it's not going to be enough, right? And then the third thing is it needs to be memory efficient. So we just discussed that if we were to pre-compute these values, store them in memory, and then print the output, it's going to take up 4 gigabytes of memory, and that's going to be bad. So our program will, like, we won't score here because we are going to exceed the allowed memory limits. So I will discuss with you another approach that we can use to solve this problem. So this is how, this is this is the thing in competitive programming competitions. We have to be creative. We need to think creatively and come up with solutions that are going to get us the solutions while adhering to these 3 things, while producing a correct answer, being memory efficient, and being fast enough. So let's say what I do is when I get this queue, I'm going to sort this one first. So I'm going to store it in another array, and I'm going to sort this one. So the sorting operation is going to take, I told you before, around n log n operations, and n log n is usually achievable for 1 million numbers. I will tell you, I will show you how you can determine if it's good or bad in the next slide, like how you can quantify whether a certain thing is good enough. So now, just for now, bear with me. Let's say we are going to sort. Let's say that we are going to have a new array q dash, which contains these same values but in the sorted order, right? Then what I'm going to do is I'm going to have a loop, right? And I'm going to have another pointer. So let's say my cursor is the pointer, right? So this pointer is going to, at over times, this is going to be like gradually increasing, right? So we are going to have 2, 3, 5, 10, 21. So my point is going to point at 2 first. Then what I'm going to do is I'm going to have our previous algorithm, that the simple algorithm which we had, this guy, right? I'm going to have it now and compute the Fibonacci number up to 2, up to the second Fibonacci number, right? So to compute up to the second Fibonacci number, we actually don't have to repeat because T1 and T2 already have the second one. So we are going to print the second Fibonacci number, and then I'm going to go to this value. Like I'm going to increment our cursor here. So then it's going to point to 3 because this is going to be sorted. So now we need to find out the third Fibonacci number. But on our simple algorithm, we have already computed up to the second Fibonacci number. And so in order to store it, we only need these 2 variables. Now we don't need a whole array, right? We just care about this maximum one and the one before it. Am I clear up to this point? So I'm going to gradually increase the value I'm going to compute, right? First, we are going to find up to 2, then we are going to increase up to 3, then we are going to increase up to 5, then up to 10, then up to 21. So now if you can see in your mind, what happens is we just we are going to have this loop at we are going to first do 2, then we are going to up the cursor, then we are going to repeat another 1 or 2 times, then another 1 or 2 times. So gradually this guy is going to come up to 1 billion or whatever the maximum value is. And while going through that, going through the computation, we are going to find out the answers. Am I clear? Do you have questions? Awesome. Right. So yeah. So we are not going to loop again because we already computed those values. So it's going to be just a linear thing, but we are checking in the middle to see, okay, what's the next stop point? What is the next stop point? What is the next stop point? Right. And sorry if I'm looking up, my monitor is here. Right. Okay. Right. So as we go on, what we do is we are going to have the answer, and we are going to store the answer in some sort of an array. Now that array is going to be only 1,000,000 items long, because q dash is going to be sorted, and we don't want to print the sorted result, right? We want to print this the results in this order. So what we are going to do is we have to store the result in some array that is going to be like 1,000,000 items long. Or another thing, if you have heard about hash maps, a hash map is something that we can use to store the result. And then finally, once we get to the maximum point, what we do is we go through this original array, and then we come to let's say we come to 2. Then from that hash map, we are going to find the second Fibonacci number, and then we are going to see 10. We are going to get the 10th Fibonacci number, and 3, the third Fibonacci number, and we are going to print it here. So hope that was clear. And the thing about the hash map, if you don't understand right now, it's fine. A hash map is something similar to an array, but in an array, like you can just what you can get is the 0th element, the first element, third element, like just only this thing. But in a hash map, you can do it's like a key value mapping. So it's like what is the second Fibonacci number? It's going to give you the second Fibonacci number within like order 1. And sorry if you don't get order thing. Order thing you'll understand it once you should read this one. So we are coming to the next section. Yeah, like Python dictionaries. Yes, exactly. So they internally implement hash maps. Right. So now, like, how do you quantify this? Like, whenever you have some sort of an algorithm in mind, how do you decide if it's going to like consume like just enough memory, and if it's going to compute like spend just enough time? You do it with this big O, the complexity analysis. And so it's a whole subject. But if you go and read this book, it's not a huge book, but like I think there was a single chapter that talks about this big O, which I think is really crucial if you are going for a competitive programming competition, because this is one of the very basic things that you need to learn. And it would be like 5-6 pages. Please go ahead and read this one, and our organizing committee, they will paste the link. Thank you. So guys, go take a look at this book. It has, I think the first chapter is about the complexity analysis, right? So after you read about it, you are going to be able to solve some problems in the IEEEXtreme competition, and a lot of other competitions as well. Right. Now I'll come to the next part. So up until now, what we discussed was not like it was pure problem solving, right? We were discussing about different approaches to solve this simple problem of finding the Fibonacci numbers, and there were different like solutions that we discussed. And in competitive programming competitions, the questions that you get could be easier than the one we discussed, and in many cases harder than what we discussed, right? So throughout time, people have discovered various kinds of algorithms, like common structures, common patterns that you can use to solve certain problems, right? And so there are common algorithms, as well as there are common data structures that allow us to solve these problems. So Akash mentioned that like you can use Python dictionaries. So Python dictionary is going to use an unnoded hash map internally, right? So those are called data structures, and we have a ton of data structures, and there's a ton of algorithms as well. So if you learn about these algorithms and data structures, it's not a finite thing. There's a limit to what you can learn given the limited time. But if you can spend some time learning some of these algorithms, especially the data structures are usually like the ones I've mentioned here. They are a bit advanced, so you might not need them. Uh, but if you can, like within the time that you have, if you can study about dynamic programming, greedy algorithms, and binary search, you'd be like a lot more ready to face competitive programming competitions than what you are right now. So where could you learn these things? It's again in that book, right? So please go take a look at that book. It's called Competitive Programmers Handbook, and it's really a handbook. It's composed really efficiently. Like it's not going to take a lot of pages. It's going to explain things simply. So you don't have to read all the algorithms and all the data structures. Just read the first few three things. So we have another question. Is that book about C++ only? No, this is like they show the examples in C++, but the concepts are not limited to languages, right? So what you need to learn are the concepts, not the language itself. So once you learn the concepts, then you can apply it in any language that you like, any language that you want to use it, right? Sorry. Okay, so I'm going to move from here. So we learned a few things. So when you go into competitive programming like competitions, when you compete in that, it's a great sport. It's a great mind sport. And when you are competing, you have to come up with creative solutions that are correct, fast enough, and memory efficient. So in order to come up with these algorithms, you have to be creative. And people have been creative throughout the time. And we have a whole bunch of common patterns and common algorithms that we can use. So whenever there's a problem, you can usually decompose that problem into like a set of different algorithms that you can combine. Or like it might, in most cases, it might not be straightforward, like straightforwardly applying the certain algorithm, but you'll have to add your own innovations into it as well. But knowing these things is going to help you a lot. So it's going to help you set up the thinking framework to like to approach these problems. So hope I was clear up to this point. Guys, do you have any questions up to now, the things that we discussed up to now? Okay, I think we are good. So now I did not go ahead and like list out a whole bunch of resources because then it's going to be too much for you guys. So start out with these two. I really recommend these two. And whenever there are competitions, I go through these two. So this first one is a book, and this is a YouTube channel. This guy is a genius, someone called Edicto. And like he has guiding videos of him solving different problems. Like he talks about the approaches. So it's good to look. It's good to look about how people solve different problems. And this guy is also, I think, discussing about some common data structures and algorithms as well. So these two links, please save them somewhere, right? So with when you go through these things, you're going to be studying, right? It's like let's say you have a maths paper, and before going to the maths paper, you have to learn the concepts. So you can learn the concepts by going through this book and watching the videos here, but you're not going to be able to make any solve any problems until you practice. So it's very similar to mathematics, because what you have to build up is that creativity, like decomposing problems and approaching these problems in a creative manner. And so in order to practice, there are many practicing sites, and something that I usually recommend is codeforces.com, because they have weekly contests, and they categorize the problems by by the algorithms that you have to use, and they add some difficulty level rating as well. And the best thing is they show the code submitted by other people. So if you if you use this is not just for for you to prepare for IEEE Extreme, but for you to continuously practice. If you use this thing, you can learn a lot from others, and you can compete in these weekly competitions. So this is one of the Hey guys, sorry I got dropped out. I'm back, right?
Yes, Mr. Pasindu.
Okay, great. Right. Okay, so you can see the screen again. Yes.
Yes, your screen is visible.
Okay, great. So now we are going to talk about preparing and competing at IEEE Extreme. So the first thing is preparing. It's fairly simple. So you have to learn the theories, learn the basics, right? You have to learn about time complexity, the space complexity, how do you calculate it, and that is how you learn how you can evaluate any algorithm that you come up with. And then learn a bit of those algorithms that I mentioned, especially greedy algorithms, dynamic programming, and learn about binary search. And the next thing is just practice. And since IEEE Extreme is a team game, you have to also practice with your team, because when approaching certain problems, you have to discuss, brainstorm with your whole team. You guys have to discuss among each other and come up with the solutions. So in this scenario, we discussed the Fibonacci sequence problem, and we had 3 approaches. So if you have 3 members in your team, maybe the three guys could try out 3 solutions and see, evaluate if they are good. So you need to practicing with your team is going to help you, the 3 of you, to sync up and coordinate better. And but for the most part, it's going to be practice, right? You have to be able to learn how to think creatively and come up with these solutions. And this is not just for IEEE Extreme, and I hope that you guys were inspired and would continue to compete in these competitive programming competitions. So continue this thing on and on. And finally, coming to competing at IEEE Extreme. So it's going to be a 24-hour long competition. So it is a marathon. So you have to be up for 24 hours. So don't waste all your energy at the start of the race, and don't get disappointed if the earlier problems are hard, right? Because you're not going to get bonus scores for submitting fast. It doesn't matter if you submit the solutions at the last minute of the competition or during the first 5 minutes, right? If you submit, and if you submit a correct, fast, memory efficient program, you're going to get scores. So don't lose your energy, keep it up, and make sure you have a good sleep before the competition, because staying awake for 24 hours is hard task for itself. But in these 24 hours, you are going to have to engage your brain. So it's not like having some Netflix binge watching thing, because you have to think and think and think over these 24 hours. You have to take a good rest before the competition. And the third thing is have some stuff that keeps you awake, like coffee, Red Bull, whatever. And the other point I mentioned, that is you're not going to get bonus scores for submitting fast. So take your time, don't lose hope, and don't get sad or anything if you don't find the answer at the get-go. You can always leave out the difficult questions and move to the easier ones, because in IEEE Extreme, during these 24 hours, you're not going to get all the questions in the at first, right? They're going to release questions every hour. So you need to be consistently up in the whole period, right? So don't get too excited about submitting too fast, right? And then the main thing is for most newbies, you don't have to write the perfect solution. So we talked that you have to write a correct solution uh, that is fast and memory efficient. But with IEEE Extreme, usually the case is that they divide the question into different parts. It's like to score 10% of the marks, your constraints are going to be in less than 10. For the next 20% of the marks, it's going to be less than 10,000. And for the rest, it's going to be less than 10 million. So something like that, right? So you can always target those brackets, right? It could be uh, the memory constraint or the input constraint, whatever it is. So there are going to be partial scores. And at the worst case, if you just can't come up with a solution that works for all, you can also do half-ass solutions, because IEEE Extreme is not very perfect, so it's not going to find out the correct solution thing. So it doesn't always have to be a correct algorithm. If it works for 50% of the scenarios, let's say you find out an algorithm that works for all the even numbers of n. Okay, that's fine. Go ahead and submit it, right? Because with IEEE Extreme, they don't have test cases enough to cover the whole thing and determine whether your solution is correct, right? So make use of that thing. And finally, don't stick to a single programming language. So it's fine for you to be pro at a single programming language, but in this competition, you are going to have to in cases try use different programming languages, because different programming languages are better at different things. For example, let's say someone is good at, so I usually program with C++, but it does not come with a built-in library to handle big numbers. That is very large integers, like 10 to the power 24, something like that. So if there was a problem that worked with those sort of numbers, I would not use C++. I would just jump into Python or Java, right? So you need to have that versatility when competing. So those are the tips and the tricks that I can teach you, and hope it helps you guys at the competition. And I hope that you got inspired. So that's about it regarding the content that I had prepared for you guys. So do you have any questions? Uh, it definitely helps to know the complexity of built-in functions. You need to know, if you're using a certain function, you need to know what's the time complexity, what is the space complexity. You need to know that if you're going to if you're hoping to score well, you need to know all those sort of things. Some programs, and you run it in the IDE. Yeah, so this could be the one I mentioned, because when you're writing on the IDE, you are usually testing against the test cases, the example test cases that they give, or a couple of test cases that you make up on your own, right? But when the program is getting evaluated, you're not going to get evaluated by these inputs. It's going to get evaluated based on the internal set of inputs that the evaluators are going to store. So in this case, like we will have like some distribution of numbers during in this range. So when you run in that whole range, if your algorithm was not correct, if your program was like even if your algorithm is correct, you sometimes have to know know if your programming language could support it. So if you if you are careful at my slides, you would see that like assume we operate on modular 10 to the power 9 cluster. So this thing I put because with C++, you can't store the 10 to the power 9th Fibonacci number in an integer. It's not going to fit. Like in 4 bytes, the maximum you can do is 2 to the power 32. But this number is very huge. Not this number, the 10 to the power 9th Fibonacci number. So like sometimes you need to be aware of like what would happen if like 2 to the power 31 plus 2 to the power 31 plus some number x happens on your program. Is it going to end up with negative values? Is it going to be undefined? Is it going to throw some errors? So you need to have that sort of knowledge regarding the programming language that you're going to use. Can we import modules like math in Python and use them? I think you can. It actually depends on the like host website. So what you have to do is like go to csacademy.com and try out. I think CS Academy has a lot of like third-party libraries as well. So the math module is something built in for Python, standard library, but you would also find some third-party libraries there given by CS Academy. So it's better to be familiar with multiple languages before participating in a hackathon. Yeah, but if you have limited time, right, and you can either focus on where is it? So if you can either focus on this thing or learning more languages, I would say focus into this side, right? So because knowing more languages is not going to help unless you are good at this. And since IEEEXtreme is is a team competition, you can definitely make use of this. So when I competed for 4 years at IEEEXtreme. And during the 4 years, like my team had, during the first year, we had a C++ guy, a Python guy, and a Java guy. So like a single person would not code in different languages, but like we had 3 people to get the job done, right? It depends. Like your strategy is something that you have to come up with based on the team that you have. And I have another comment on new to coding competitions. Will we get a processing time difference in online IDE and an offline? Okay, so usually the processing time, it's like when you study the big O notation, you will understand that it's not usually going to depend on your machine and the remote machine, because like we are talking about the differences in algorithms. Like some algorithm might compute its answer in order n squared, while some other algorithm might compute the answer in order n, or something could be doing it in order log n. So those 3 algorithms, as n grows up, they are going to take very vast, like going to be vast differences between the 3. So the difference between difference when running in your local machine and remote machine, it's not going to impact much. So it's not going to matter. What matters is the time complexity of the solution that you are writing. And once you are really good at this, then you can think about further optimizing. So for example, in order to sort a list of numbers, you can write a program that takes order n squared. Order n squared is something like n squared operations, uh, a multiple of n squared operations. And another algorithm you could write in that takes order n log n, that is like n into log n operations. And when you compare the number of steps taken by these two algorithms as n grows into the higher numbers, it is not going to matter. Like, these are two kinds of algorithms, and the person who writes the n log n version is going to outsmart the one who writes the n squared algorithm, and like this thing would score. Okay, do we have any more questions? What kind of math topics? Learn about modular arithmetic if you have time. Then like in general number theory. Yeah. So this book, it has the math topics as well. So this is like the solution. Just go through this book. Okay, do we have any more questions? Okay, I think we are good now. So organizers, back to you.
Thank you, Mr. Pasindu, for your sharing for your knowledge and giving a marvelous workshop experience to this virtual audience. So please accept our virtual token of appreciation on behalf of our team.
Thank you.
And I would like to invite you all to take a group photograph as well. And we will give you 2 to 3 minutes to get ready for the photographs and turn on your cameras as well. Hope you all are ready now. And let's take a count. 2, 3, 2, 1. Okay, thank you. So thank you everyone for your participation for our workshop on how to your participation. Thank you.